In the year 775, something hit Earth, not an asteroid, but not a comet, something worse. We know this because trees remember. Deep in the growth rings of 1,000-year-old cedars, scientists found a spike, carbon 14 levels 20 times higher than normal for 1 year, 775 AD, and in Antarctic ice frozen for 12 centuries. The same signature, beryllium-10, nitrate deposit, all pointing to the same event. Earth was hit by radiation from space, from a star. 1,200 light years away, and the radiation pulse lasted 3 seconds. 3 seconds. If that burst had been 10 times stronger, or pointed directly at us, or lasted 10 seconds longer, you wouldn't exist, because your ancestors would have died. A dying star, 1,200 light years away, exploded, and for 3 seconds, it fired a beam of energy equivalent to 1,000 supernovas all at once in one direction toward Earth. Why a gamma ray burst is dangerous? Because it's an invisible cosmic laser that can sterilize planets. To understand the danger, you need to understand the weapon. A gamma ray burst begins with a star, not just any star, a hypergiant, 50 times more massive than our sun. For millions of years, this star burns hydrogen, then helium, then carbon, oxygen, silicon. Each fusion reaction creates heavier elements and requires more energy until the core is pure iron. A core the size of Earth collapses to the size of Manhattan. Supernova releases 10 to the 46 joules of energy. That's a 1 with 46 zeros, for comparison. Every nuclear weapon on Earth combined is about 10 to the 18 joules. A supernova is 10 billion times more powerful, and a gamma ray burst is 1,000 times more powerful than that. But here's where it gets worse. As the core collapses, the star's magnetic field compresses, intensifies, creating a magnetar, the most powerful magnet in the universe. This magnetic field channels material into two beams, shooting out from the star's poles. So 99.999% the speed of light. Each beam carries the energy of 1,000 supernovas, focused, collimated, like a laser, and if that beam points at your planet from anywhere in the galaxy, you die. There are two ways a gamma ray burst kills. The first, direct hit. If the beam points directly at Earth, the gamma rays don't just heat the atmosphere within hours. 50% of Earth's ozone layer is destroyed within days, 75%, and without ozone. Ultraviolet radiation from the sun increases by a factor of 10. Plankton die first. UV radiation destroys their DNA, then the fish that eat plankton, then the fish that eat those fish. Within 6 months, 70% of ocean life is dead. On land, plants can't photosynthesize under intense UV. Harvests fail. Famine spreads. Within 2 years, 90% of humanity is dead, not from the burst itself, from the collapse of the food chain, the second way. Glancing below, this is what happened in 775 AD. The beam didn't point directly at us. We were 20 degrees off axis. We received only 5% of the beam's full intensity, 5%. And it still left a signature in tree rings that lasted for centuries. In 2005, two astrophysicists published a hypothesis: a gamma ray burst from within our galaxy 6,000 light years away, pointed directly at Earth, The timing matches, the extinction pattern matches, marine life near the surface died first, exactly what you'd expect from ozone depletion. We can't prove the Ordovician extinction was caused by a gamma-ray burst, but the evidence is compelling and terrifying because it means this has happened before. To Earth. Could happen again. So the question becomes, are there any stars in our galaxy that could do this, and are any of them pointing at us? A Wolf-Rayet star 8,000 light years from Earth. In the constellation Sagittarius, mass 25 times the Sun. It has a companion star. They orbit each other every 220 days. And as they orbit, the stellar wind from WR104 creates a spiral pattern, a cosmic pinwheel visible from Earth with large telescopes. But here's the problem. The rotation axis of this system might be pointing directly at Earth. We don't know for certain. The angle is difficult to measure. From 8,000 light years away, estimates range from 0 degrees off axis to 40 degrees. If it's 0 to 20 degrees, we're in the danger zone. If it's 20 to 40, we'd receive a glancing blow, and WR104 could explode at any time. Could have already exploded 8,000 years ago, and the light is still traveling toward us. We simply don't know. What we do know is that when it does explode, if it produces a gamma ray burst, and if that burst is pointed at Earth, we will have approximately 8,000 years warning, which is to say, none, because the gamma rays travel at the speed of light, and the light that tells us the star has exploded travels at the same speed. We would see the explosion and receive the gamma rays simultaneously. The first sign would be a flash brighter than the full moon, visible in daylight. 3 seconds later, every gamma ray detector on Earth and in orbit would trigger within an hour. The atmosphere would turn brown, nitrogen oxides forming within 6 hours. The ozone layer would be measurably thinning, UV radiation increasing, and there would be absolutely nothing we could do. Ida Karina, 7,500 light years away, 100 times the sun's mass. That wasn't a supernova. That was a warning. Betelgeuse, 640 light years away. The shoulder of Orion, visible to the naked eye. In 2019, it dimmed dramatically. Astronomers thought it might be about to explode. It didn't. It was a dust cloud. But eventually, Betelgeuse will go supernova. Fortunately, its rotation axis doesn't point at Earth. We'd see a spectacular supernova, but no gamma ray burst. So how often do gamma ray bursts happen? In our galaxy, astronomers estimate 1 gamma ray burst every few million years. Observable universe, zoom out. But in the observable universe, we detect one. Every day, every single day, Somewhere in the universe, a star dies and fires a beam of death across the cosmos. The kill radius of a typical gamma ray burst is 6,000 light years. Our galaxy is 100,000 light years across, which means most GRBs that occur in the Milky Way wouldn't threaten Earth unless the burst originates within 6,000 light years of our solar system. The probability of that in any given year, approximately 1 in 10 million, which sounds safe until you consider that complex life has existed on Earth for 500 million years. 500 million years divided by 10 million equals 50, meaning Earth should have been hit by a lethal gamma ray burst approximately 50 times. Since complex life began, and when we look at the fossil record, we find 5 major mass extinctions, plus 20 smaller ones. Not all of them can be explained by asteroids or volcanoes. Several have no known cause. Could some of them have been caused by gamma ray bursts? We have one confirmed candidate, the Ordovician, possibly the Devonian, late Cambrian. We may never know for certain because gamma ray bursts don't leave craters, they don't leave ejecta, they leave only a pattern of death in the fossil record and fear in the present. If a gamma ray burst is heading toward Earth, this is our early warning system, such as it is. The Neil Gehrels Swift Observatory, launched in 2004, orbiting 600 kilometers above Earth, designed to detect gamma ray bursts anywhere in the sky, and slew its telescopes to observe them within seconds. The Fermi Gamma Ray Space Telescope, broader sky coverage, lower sensitivity. Together, these two satellites detect about 1 gamma ray burst per day from across the observable universe. But here's the problem. Gamma rays travel at the speed of light. So does the light that would warn us. The burst is coming. They arrive simultaneously, which means the first warning we would have is when the detectors trigger, which would happen approximately 3 seconds after the burst hits Earth's atmosphere. 3 seconds. CDR, Rodriguez. People ask me, couldn't we detect the star before it explodes? We wouldn't know if it would produce a gamma ray burst, or which direction. That burst would fire. Space is 3-dimensional. The odds of a beam pointing exactly at Earth are extraordinarily low, but not zero. So astronomers watch observatories around the world monitor Wolf-Rayet stars, analyzing their spectra, looking for changes, tracking their brightness. But the best warning we could hope for is maybe days, maybe weeks. Not enough time to evacuate a planet, not enough time to build shelters, not enough time to do anything except watch and wait. Right now, somewhere in the Milky Way, there are stars dying. Wolf-Rayet stars, hypergiants, blue supergiants, each one. A potential gamma ray burst, each one. A cosmic roulette wheel spinning, pointing in random directions. The odds that one points at us are low, but not zero. We know this because it's happened before. This is what it means to live in a violent universe. Galaxies collide, stars explode, black holes devour worlds, and occasionally a beam of energy, equivalent to the Big Bang itself, slices across space and ends everything in its path. But here's what we do know. Earth has existed for 4.5 billion years. Life has existed for 3.5 billion years. Complex life for 500 million years. And we're still here, which means we are the descendants of the lucky ones, the ones who weren't in the path when the beams fired. Will our luck hold? No one knows. Humanity chooses to look up, to understand, to witness, and to hope that when the next beam fires somewhere in our galaxy, it points anywhere. But here, gamma ray bursts occur approximately once per day in the observable universe. The nearest known supernova candidate is 640 light years away. We watch for all the species that weren't as fortunate.